Today, we're going to talk about a really beautiful idea for solving problems. It's called dynamic programming. And really, it's less about attacking a problem head-on and more about, well, a quieter, more thoughtful approach. And we can start with a little puzzle that you see literally every single day, but probably have never really thought about. Have you ever just stopped and wondered, when you're reading something on a screen, how does the computer know where to break the lines? How does it make a whole paragraph look so balanced and, just easy to read? Believe it or not, this actually has a name. It's a classic computer science challenge called the printing neatly problem. And it's one of those amazing little puzzles that our computers are constantly solving for us, quietly, in the background, making all these tiny decisions so that our reading experience just feels effortless. So, it all comes down to defining what neat really means. You can think of it as a quest to minimize ugliness. Seriously. We can actually give a score to the ugliness of a line based on how much empty space is left at the end. Too much space and the whole paragraph looks jagged and messy. So the computer's job is to make a series of line break choices that add up to the most beautiful, least ugly paragraph possible. So how does it do it? Well, the most obvious way, what you might call the brute force approach, is to just try every single combination. Okay, let's break the line after the first word. See how that looks. Now after the second and the third. And just keep doing that for every single word. Yeah, you can probably see the problem here. This gets out of hand fast. The number of possible ways to break up a paragraph grows exponentially. That means for every single word you add, the number of possibilities pretty much doubles. We're talking about an astronomical number of combinations, way too many for any computer to check. This approach is just too loud, too clumsy. We need a smarter, quieter way to solve this.
And that brings us to the first big idea behind dynamic programming. Instead of trying to wrestle with this whole giant problem all at once, what if we just focused on solving the smaller pieces of it first?
Now, this has a fancy academic-sounding name, optimal substructure. But the idea itself is actually super simple and intuitive. Think about building with Legos, right? The best, most awesome castle is going to be made from the best walls and the best towers you can build. In other words, the best solution to the big problem is made up of the best solutions to its smaller parts. So let's bring that back to our paragraph. To find the absolute best way to format the entire thing, you first have to know the best way to format the paragraph without its last line. The perfect overall solution is built on top of the perfect solutions for all the smaller chunks that came before it. It's kind of a comforting thought, isn't it? The idea that you can solve some huge, overwhelming problem by just focusing on making the wisest possible choice for each small part along the way. Okay, but this approach has a potential problem. If we're breaking this big problem down into all these little pieces, we might end up solving the exact same little problems over and over again. And that brings us to the second big idea. This is the concept of overlapping subproblems. In our paragraph example, figuring out the best way to format, say, the first 5 words is a subproblem. And it's a subproblem we might have to solve dozens of times as we're trying out different options for the rest of the paragraph. Doing that same work again and again is just incredibly wasteful. I mean, imagine your teacher gives you a math test, and the question, what's 5 times 7, shows up 10 different times. Are you going to recalculate it from scratch every single time? Of course not. You'd solve it once, and then just remember the answer. It makes no sense to do otherwise. And this leads us to the really simple, elegant solution that's at the heart of dynamic programming. This is the aha moment that makes everything click. The question is almost beautifully simple. What if, the very first time we figure out the best way to format those first 5 words, we just save that answer somewhere? This technique has a great name, memoization. And no, that's not a typo for memorization, though it's close. It actually comes from the word memo, like you're writing a little note to yourself for later. You solve a problem once, you write down the answer in a memo, and if you ever need that answer again, you just look it up. No more redoing the work. So what you end up with is basically a cheat sheet for your problem. For every little piece, like how to best format this first sentence, you calculate its cost, its ugliness score, just one time. Then you store it. And from that point on, whenever you need that information, you don't recalculate. You just look it up. It's instant. And it saves a truly enormous amount of work. So here's the crucial insight. Since we don't know exactly which small problems we're going to need to solve later, we just solve all of them once. We start with the smallest pieces and work our way up, storing all the answers in our table. It's a method of patient, thorough preparation. Okay, so we started with a simple little problem about making text look pretty. But why does this one quiet idea matter so much in the grand scheme of things? Well, because this exact same logic, this same approach, is used to solve some of the biggest and most complex problems in the world. This whole technique of breaking a problem down and remembering the answers, it's working silently all around you, all the time. How does your GPS find the absolute fastest route to your destination? How do scientists compare massive DNA sequences to understand diseases? How do huge logistics companies figure out the most efficient delivery routes? The answer, at its core, is this same patient, quiet logic. It is a fundamental tool for solving really, really hard problems. So let's zoom out for a second for a final thought. Because dynamic programming, it isn't just a coding technique. It's a way of thinking about problems. It's a quieter, more considered approach. See, a lot of the time, we're tempted to use what's called a greedy approach. We just make the choice that seems best in the immediate moment, the thing that's locally optimal. But dynamic programming is different. It takes its time. It solves all the small problems first so that it can absolutely guarantee it finds the truly best overall solution, the one that's globally optimal. It resists the easy, obvious answer in favor of the best, long-term one. And I think maybe that's the real takeaway here. The best path forward, whether you're writing code or just living life, often isn't the one that looks easiest right now. It's not the one that offers the quickest reward. It's the one that's patiently built, piece by piece, from the best possible small steps. Thanks for taking this quiet walk with me today.